So hello and welcome to this tutorial, which is going to analyze how we establish pH for a weak base. I'm not creating a separate one for Ka because as we work through it, it's effectively the same process. A couple of differences, one being that we are obviously doing this for a base, and so there's going to be the production of the hydroxide ion. The other one being, if we're calculating the pH, we are going to have to first calculate the pOH because we're dealing with the hydroxide ion. Before we go on and ultimately calculate the pH. So there are a couple of different steps as we go through it, but effectively the process is the same. And like all of them, we start with the equilibrium equation that we have here. So we can establish that this is a weak base, first and foremost, because it doesn't contain a hydroxide in the actual formula of the base itself. So here, as we're dealing with methylamine, you can see here that there is no hydroxide in there. It's not a metal hydroxide of group 1 or group 2. So it's not a strong base. In addition to that, if we take a look at our values of Kb, we can see that there is a relatively small Kb for this, and so it's going to ionize only partially. Now notice again that I said ionize for this. It's not just acids that ionize. Some weak bases, in fact most weak bases or all weak bases are going to ionize as well. They don't dissociate completely into their ions. They do only partially ionize. So ionize is the correct terminology here when we're dealing with how a weak base ultimately goes to form the hydroxide ion. So you can see this is the equilibrium equation that we are going to start with. So with any calculation, we want to start off with the initial pieces of information that we know. We know that we are starting off with initial concentration. So we're going to treat this again like an ice table. We know that we're starting off with an initial concentration of 0.250 moles per liter. Now again, because we're using an equilibrium constant here, I'm not going to put the units into my ice table because ultimately until we get to the end and establish the hydroxide ion concentration, we don't necessarily need to use the units here. The other thing that we do know is, or I guess the other thing that we can look up, is the Kb of the methylamine. And so if you look it up either in the appendix at the back of your textbook or on the reference sheet that you were given, you will find that, at least under the conditions we have, that the Kb of this particular substance is going to be 4.6 times 10 to the negative 4. Now again, keep in mind that every single K that we deal with is products over reactants. So what this tells us, being a relatively low Kb, is that it lies to the left and we are not going to see a relatively high concentration of either one of the product ions. So it is a weak base, or at least the Kb will confirm that it's a weak base. So now we're just going to fill out our ice table. We're going to make the assumptions that the initial concentrations of the product ions are both 0, that the only way that the methylamine can go is down, and that the only way that the product ions can go is up. Now what you're going to notice for pretty much all acid-base equilibria scenarios for weak acids and bases is that the ratios are nice. That is, they all stay 1 to 1 to 1, at least for the time being anyway. And now we've established our equilibrium concentration of the original reactant base, which is again the methylamine, and we can see that it's going to be 0.250 minus x. So now we have all of the equilibrium concentrations that we need for our equilibrium expression and ultimately our calculation. So now it's just a matter of writing out our Kb. Now it's no different than any other equilibrium constant that we've done. We are going to take the concentration of the products, in this case the concentration of the product ions, and we're going to divide it by the initial concentration of the methylamine. Now notice that we're not including water here. Remember, water is a liquid in this state, so it's going to remain relatively constant also because we are in an aqueous environment. There's already a high concentration of water, so it's not going to be appreciably affected here. The other thing I want to point out is that we do have a relatively low K. Now anytime we have a relatively low K, we can do the test to see if we can negate a value from x from any value that's not 0. So our test is no different than it is for any other type of equilibrium expression. Our test is the initial concentration over our equilibrium constant. In this case, if we do that, our initial concentration, and the only concentration that we've been given, is 0.250, and our equilibrium constant, or value for K, is 1 times 10 to the negative 4. Now in terms of Ks, that actually is a relatively high K, and if we had a fairly low concentration, I don't think we'd actually be able to negate X. So as we can see in this case, our test value does exceed the benchmark of 500, so it is okay to negate X here. And all that means is that once we go through this calculation, our X value is going to be small enough that it's not going to appreciably affect the initial concentration of our base here. So now it's just a matter of plugging in those values. The two values in our numerator are both going to be X, and the value in the denominator is going to be our initial concentration of base. Notice again that we don't need to include the minus X because of our test. So as I'm simplifying here, I'm going to take my two X values, multiply them together to get my X squared value. I'm going to take the concentration of the base in the denominator. I'm going to multiply that by the Kb of the base. And now to further simplify, I am going to take the square root of both sides. And ultimately that's going to leave me with a value of X of 1.07 times 10 to the negative 2. Now you might be looking at this value and saying, well, the Kb has two significant figures, so shouldn't my X value have two? And the answer to that is yes, it probably should at this point, but I do want to keep my precision a little bit because I do have to use that X for a subsequent calculation. So not only have we calculated the value for X, but we've also established the concentration of the hydroxide ion. Now this question is asking me to figure out the pH of the solution, and there are a couple of ways that I could go about doing this. I could take the hydroxide ion concentration and put it into the equation involving Kw and hydronium in order to solve for the hydronium ion concentration and go from there, and you can absolutely do that. But I think what I'm going to do first is I'm going to calculate the pOH of this particular solution. So in calculating pOH, it's just the negative log of the hydroxide ion concentration. So in this case, we are going to take the negative log of 1.07 times 10 to the negative 2. Again, understanding that this has two significant figures, or at least we should be carrying forward this answer with two significant figures. And in doing so, I get a pOH of 1.97. Now again, we look at 1.97, that is not three significant figures, that's actually represented in two. Only the numbers to the right of the decimal place are considered significant here. So this is where I've finally dropped it into my two significant figures. Now you'll notice that this is a low pH, which makes sense because it is a base. This is not a low pH, it's not indicating that this is acidic, this is a low pOH. What we are going to do now is calculate the pH of this solution. So pH is equal to 14 minus the pOH. So in this case, we're going to take 14, we're going to subtract the pOH value that we got, and we are going to resultingly have a pH of 12.03. So even though this is a weak base, we can see with fairly high certainty that we have a basic solution here. That is, the pH is significantly greater than 7. Now the important thing to remember, especially with weak bases, is that perhaps we don't see the hydroxide ion concentration in the formula itself, but it produces hydroxide undergoing the reaction, and as a result is ultimately going to be, as we can see here, a basic solution. Now I didn't go through a Ka calculation. There are a couple of differences though, one being that you're not producing the hydroxide ion concentration, you're producing the hydronium ion concentration. So ultimately when you go to calculate the pH, there's not that additional step of first figuring out the pOH, for example. But pretty much everything else in terms of the steps, the way that we set up the ice table, the way that we go through our K calculations, the use of the test, all of these things are effectively going to be the same. So as you go through a Ka or Kb calculation, we treat it as we would any other type of equilibrium scenario, and these are the basic steps that you would use to solve for pH or pOH, depending on whether you're dealing with an acid or a base, or depending on what you've been asked to find, I suppose, in the question. So some questions like this will also ask you for something called percentage ionization. Now what your percentage ionization is really just asking is what percentage of the original base or acid has ionized and formed ultimately hydroxide ions, or in the case of an acid, hydronium ions. So in this case, the way that we establish this and the way that it's calculated is that we take the concentration of basically X, which is either going to be our hydroxide ion or our hydronium ion. We are going to divide that by our initial concentration of the acid or the base, and we are going to represent that as a percentage. So it's basically going to be the concentration of hydroxide or hydronium ions over the initial concentration of the acid or the base that we're using. So in this case, our X value we determined to be 1.07 times 10 to the negative 2, keeping in mind that that was two significant figures, over the concentration initially of 0.250, we are going to express this as a percentage. And in doing so, we're going to get a value at least to the appropriate number of significant figures of 4.3%. So what that ultimately tells us is that in this particular solution, under these particular conditions, 4.3% of the original base concentration is going to ionize to produce hydroxide ions. So when you come across a question like this, that's not only asking you for the pH or the pOH, it's asking you for percent ionization. All it is just what percent of the original concentration of acid or base has ionized to form hydronium or hydroxide ions. And in this case, being a base, we are figuring out what concentration of the original base ultimately forms hydroxide ions. As we can see here, it's about 4.3%. So this value further confirms for us that this is in fact a weak base, because very little of it is actually going to form hydroxide ions. So hopefully after watching this, you have a better understanding of how we can solve for the pH or the pOH of a weak base using Kb, how you can figure out the percent ionization of a weak base, and then perhaps how you could extend this format and this procedure to solve for the pH and the percent ionization of a weak acid. Thanks for watching.